All right, I think it is recording. Right. Recording. Good morning or good evening or good night, everyone. Thank you for joining us in this exciting presentation by Professor Wasim Jabi. If you haven't heard about him, he's one of the pioneers in computational design, particularly applications in architectural design or built environment design domains or disciplines. Professor Jabi is the course director of the MSc Computational Methods in Architecture program at Wells Schools of Architecture, Cardiff University in Wales, the United Kingdom. And he has been teaching in different universities across US. And before he moved to United Kingdom, after he received his MA and MSc PhD degrees from University of Michigan. He has won several funding awards for his famous research that he will present today. I don't want to take much of your time. I shared already his information about his background. Also today's talk as well, which will be titled "The Graph Behind the Building." Thank you, Wasim, for taking time and joining us and presenting your precious work with us, valuable work with us. I'm going to turn off my video and it will be your presentation. And remember that this session is being recorded. Meanwhile, if you have any questions, please type on the chat. I'm going to ask at the end of the presentation. Wasim, would you like to answer questions during the presentation as well?
I don't mind. You can interrupt me, ask questions. Happy to do. Yeah, any I'd like it to be more, as I said, more interactive and more casual.
Okay, excellent.
Or
we'll do that.
Yeah.
Excellent.
Cool.
Okay, then can we test before I turn off my camera your presentation?
Oh, sure. Yes.
Is there any sound?
No.
Okay.
Let's see if I can share this. And if I do this, is that visible?
It is. Excellent.
Yeah, perfect.
See you later.
All right.
You will be talking to black boxes, but...
Oh, don't worry, I'm used to it. It's been a couple of years now.
See you later.
Thanks. Halil, first of all, thank you very much for inviting me, and thanks to Rob Woodbury, who has been both a friend and inspiration for many, many years. And really a lot of the work that I do today stems from early research that has been done by the likes of Rob Woodbury and others who were looking at fundamental issues of how you deal with design and how you represent design. And now, of course, how we fabricate design. So I titled this talk, "The Graph Behind the Building." And it is actually due to a literal image that I put on LinkedIn, which you will see a bit later in the presentation, where I put a graph behind a building. And that LinkedIn post, and I think also it was a tweet, gathered a little bit of discussion and reaction. So obviously there is something that people got attracted to when we talk about a building or a model of a building, the representation of a building, and then the logic of a building. And those to me are two very different things that we need to address in different ways. So I will explain all of that, but bear with me while as I said, this is not a canned presentation where I've done the work, published it, and here now I'm just talking about it. It's really an ongoing and active research program that I'm pursuing, and I'm trying to wrap my mind around it. So I would appreciate any feedback that you can offer. But let's start with the basics. So let me just present this to you. So imagine you have this line, and on this line you have these weird, dots, these black dots, and some of them are labeled A, B, and C, right? If you look at it at a very kind of primitive level, you can say, yeah, it looks like if I take a ruler and measure, that B is closer to A than C is to A, right? C is like far onto the right. And if you are dealing only, or if your framework is only geometry, that is 100% accurate. Yes, I can measure it and I can tell you by numbers that B is closer to A than C is to A. But there is more to it when we are talking about changing your framework, changing the frame of mind. So when we are talking about topology, and topology means how things are connected to each other, just simply adjacencies and networks and how things are connected to each other. In reality, topologically speaking, B is further away from A than C is from A. And it all has to do with these strange black dots that I have put there. That's where that kind of trick is. You will notice that there are more black dots connecting A to B than connecting A to C. Now, in topology, geometry usually does not matter. What I am saying here, topologically speaking, is that I have to go through multiple nodes in order to get from A to B. So B is at a greater depth to A with respect to A than C is to A. Now you can say, well, yeah, but that is kind of way too abstract. So what does it matter that there are more points? Those points can be very, very significant. So if you move away from geometry into topology, but then you move from topology into semantics, those dots become really important. So what do I mean by semantics? Information, the fact that there is a meaning to these dots. They're not just abstract dots, there is an actual meaning to them. So here is one piece of information that I put in there. I said that the first dot is a construction site, and therefore it is there is a stoppage in traffic. And the next dot is a red light that takes forever to turn green. So all of a sudden, I'm talking about roads, right? I'm talking about vehicular roads. And you know that perhaps two cars that are starting in opposite direction from A, one goes to B and one goes to C. And let's assume that from A to C, it's a highway. That person going from A to C can get home faster than the person trying to get from A to B. So not only is the geometry now irrelevant, it is the topology, because he has to stop at different intersections. And what those intersections are, semantics, makes a big difference. And this is what we are trying to kind of unravel when we are looking at how buildings are connected, or how spaces in buildings are connected. Because we know that some spaces I can get to from my office very easily, where the water cooler is or where the coffee machine is. And some spaces are further away, even though they might be just around the corner, because maybe there's a crit going on in the corridor and I cannot pass, right? So topology, semantics, geometry all play a part in the final kind of logic of navigation. And as Rob said, this is not new. This is very old. I firmly believe that buildings are a graph, some kind of a graph, or actually perhaps even a multitude of graphs that are all layered and connected to each other. But it is really important to think about it in a more abstract way. Rob in his book talks about abstraction, talks about a jig, talks about controllers. And these are all, to me, these three concepts of abstraction, jig, and controller are ways to not deal with the object itself, which BIM does, and that has a lot of disadvantages and complexity, but deal with the logic of it. What is behind it? Because those can give you abstractions that are very useful for you to manipulate. So this image, this very, very old image from 1974, from Harrod, who, again, that image was used by Nicholas Negroponte in his book, Soft Architecture Machines, talks about, and it's called houseness, meaning what is the nature of a house? And it is almost the precursor for what we call now industry foundation classes, what makes the components, how they're connected, and spaces, and how they are connected. I can't really read it all, but if you would like, go see the original. And you can see that they're trying to draw relationships between both physical components, but also non-physical components like space. Space is really difficult to deal with, like a room. What is a room? Where are the boundaries of a room? and how that can be interconnected. So this is way back to the 70s. And obviously there was a lot of work in the 80s as well. I was lucky enough to be at the University of Michigan in starting in 1989, where I did my master's and then continued for my PhD. And the professors that I worked with, Harold Borken and Jim Turner, and then also a PhD student, Ted Hall, they were working on how to represent buildings and spaces in buildings the right way. And that instilled in me that idea of how do we represent things. And I was unhappy that we are representing things using, the components, the physical components, the walls and the foundations. That will help you build it, but will not help us as architects design it. So what is a graph? Let's start with the basics. A graph is a data structure. Obviously, it's made out of nodes, or what we call vertices, and that are connected by edges, or at least some of them can be connected by edges, some of them can be isolated. And those edges represent a relationship between them. So the node usually holds kind of information about some object, some actor, some movie, some car, some engine size, whatever it is. And then there is a relationship. So this is a graph of whatever, it's the matrix and the actors that acted in the different sequels of the matrix. Vertices and edges can have labels and extra semantic information attached to them, and vertices can be connected by more than one edge, obviously. A person can be the mother of another person, and she can be also the sister of another person. So they can have multiple relationships. And edges in graph can be directional, that's called the directed graph, or non-directional, which is bidirectional. So you can see here, the intermediary is a shareholder of the entity, and the intermediary is also can be the director of an entity, and it's all directed. But obviously, an entity cannot be the director of an intermediary. So that's when you need a directed graph, when the relationship cannot be reciprocal. One person is the parent of another person, but this person cannot be the parent of the first person. But once you have built your graph, you can actually use it, you can mine it for information, usually using a graph query language, which sometimes they call it a cipher. So you can see here kind of an example of that cipher, and you can mine that information quite efficiently. I've read recently that the complexity and the time it takes to mine a graph has nothing to do with the size of the graph. You can have millions of nodes. It has to do with how much of that graph you have to traverse. So it's a very efficient way, because you just have to find the neighborhood that you are in that you need to traverse, and that will affect the time to get the reply back. And once you have graph theory, especially when you apply it to buildings, you can spawn all sorts of research areas. And one of them that has been going on now for some time, sometimes maligned, sometimes loaded, you'll make your own opinion about it. I don't pretend to be either a supporter or a naysayer regarding it, is the idea of space syntax. And you can see it in the wording, that it's about space, and it's about the syntax of the space, the logic of it, or how it is formed as almost as a language. And what you see here is basically, I think it's probably centrality or something of the sort. But what they don't show you is that behind this floor plan is basically a gridded graph. It's just a big grid of graph where every point on that grid is looking at its connectivity to all the other points in that space, and finding out how well connected or how isolated it is from all the other ones. And so you can run these algorithms really, really quickly and get a total measure, and then you can spread those numbers over a spectrum of colors, and you can present that to the user. So you can find out whether if you have designed a building, where are the points of congestion, perhaps, and you can imagine, the entrance and the control that is at the entrance. That's where all the people are going to be funneled in. It's not that difficult to predict that. But also, where are the areas that are perhaps very isolated and you need maybe more, surveillance on them, or change the design so that you integrate them a little bit more. So it becomes really useful to just look at the structure of the graph and finding out information about it. So graph theory becomes really important and really useful. If you're dealing with GIS, geographic information systems, they are all about topology. They're all about whether a point is in an area, whether this plot of land is next to a street or next to another plot of land, and how do you get from point A to point B? And they do it obviously in different layers. And we're actually looked at GIS systems, and we are now trying to integrate what we are doing with GIS systems as well. Now, compare all of this, what I've been talking to you about, with building information modeling. Now, BIM systems are absolutely great, right? They allow you to model everything in a lot of detail, assemble everything, federated models, building components. You can collaborate on it and build it and send it to construction and do all sorts of analysis. And perfect, great. But there is a reason why they happen much later in the design process and why they fail so miserably in the conceptual design phase. They're not, obviously, they're almost not used in the conceptual design phase. Even though some not to be named software tells you we have conceptual masses and we have conceptual design support and all of that, really they are not built for it. And the reason they are not built for it is that what is missing is space. Is the main ingredient that architects, the bread and butter of architects, is space. And how you design space. And it's not that we can draw space easily, but we think about space. So we think about spatial relationships, and we think strategically, right? We've all, if we're architects, we all remember a sketch on a napkin and say, we don't put, 30-centimeter walls or 20-centimeter walls. We put a single line, right? And we quickly draw zones and relationships, and we strategize. That sketch is basically not just an abstraction, it's a strategy document. And there is no strategy when it comes to BIM. BIM tells you, I've opened up my Revit tutorial when I was learning Revit. First step is put your foundation. The second step, put the slab. Third step, put the walls. So you are already driven into making the building components, which is fine. But then it is not about strategy. It's not about design. It's not about how things, and it doesn't give you information back. It's not feeding back to you what you are doing and whether you're doing it the right way or whether you want to change something. So you end up with mistakes that are hidden that show up much, much later in the design process. And that becomes very, very late. Then there is this thing called industry foundation classes, and it came out of product modeling, step PDES modeling that my professor Jim Turner worked on, in the 90s, in the early 90s, and it's great. IFC as not as a file format, because as file format it's horrible, it's horrendous. You can't deal with it. I've been trying to deal with it for a long time, but as a schema, it's amazing, and it also can represent conceptual things that are not virtual elements. It also has graphs in it. You can actually have an IFC graph in it, but people don't use it that way. And the big commercial companies are not interested in using it to its full extent. They just want to pay lip service to it. So you'd end up with a lot of failures and a lot of people complaining about IFC simply because the people who are writing IFC files are doing a half-hearted job about it. But in fact, anything that I'm doing in my own software, which is all about graphs, can all be represented in IFC. I don't do it because it is so difficult to deal with, but it has all the components. I just wanted to point that out, that IFC as a schema, as an API almost, is amazing, is really amazing. And we should pay more attention to it. And I would love to see more software that uses it. So this is a graph that is a representation of an IFC schema, where all the object relationships are there. It still has the mainstream IFC, still has a focus on building components because they have to talk to the BIM managers and architectural firms. But actually, you can also have conceptual spaces built into it. And you can connect them. It does not restrict you in any way. It's an open schema. So I think I have established that graph is equal to a topology, right? That these two things are perhaps interchangeable, or a graph is the best way to represent a topology, or it's the purest way of representing a topology. It's the most natural formal structure that can represent how things are connected. So we obviously, it goes to reason that we need a system that has topology and semantics at its heart, so that it can represent a design project's geometry, topology, and information in one coherent system that can be queried. And we have invented such a system, and we call it Topologic. So let me tell you a little bit about Topologic if you have not yet heard about it. So this is a much more advanced stage of Topologic, where we have taken, and as I said, I'm going to jump a little bit. This is the tweet and the LinkedIn post that I told you about. This is what you're seeing on the left side is a building, quite, very monstrous building that came from a piece of software called TestFit. So TestFit allows the state developers to look at a plot of land and very quickly put units and calculate densities and setbacks and put parking and find out whether it's economically feasible, et cetera, et cetera, et cetera. It has also, TestFit has been criticized that the architecture it's creating is not very inspirational, but that's not my business. Architects can accept it or not accept it, that's up to them. But it created models that are very compatible with Topologic. So it was a really nice kind of test bed for us to bring their models into Topologic and see what we can do with them. So I tweeted an image very similar to this one. I think I just simply changed the colors on it, where you can see this yellow lines that are in there, and that's what we call the dual graph. So a dual graph is another type of representation of a building, of connected spaces. And I will get into a bit of the maths of it, but don't worry about it. Basically, any space can be represented by a vertex. And if it shares a surface with another room, another space, you draw a relationship line. And you keep doing that, and you connect everything. You connect the rooms to the corridor to the elevator down to the garage, to the restaurant, and you build your network. But once you have that network, it's not just a beautiful kind of looking, graphic. You can actually traverse it. You can find shortest distances, you can find centrality, you can apply space syntax. All of these things become readily available if you can build that graph. And the trick is in building that graph, because BIM data is notoriously inadequate for building graph data. BIM systems, even though they tell you they have all the information, are ad hoc systems. Some things have graphs and connectivity. Some things are isolated and just parameters. And some things need scripts for you to write in order to find the relationship. And this kind of ad hoc way of doing things ultimately leads to a lot of frustration and inefficiencies. So this is the tweet. This is the LinkedIn post and the tweet, which is the graph behind the building. So what you are seeing in the background, which looks like this kind of anonymous kind of network, is the graph of that building that you see in the foreground. And it's just a different representation. It's not meant for human readability. As humans, we can see this building, and we can imagine its scale and size. We can imagine living in one of those units or not living in one of those units. But the one in the back is all about information. It's all about mining information. But that is the structure that we need to get to when we are doing BIM systems. So you can read that one in the recording. I'm not gonna go through it. But let me introduce to you a little bit more formally Topologic. And this is a simple version of what you've seen before. So what you are seeing here is obviously an abstraction of a building. It looks like a building, some kind of L-shaped building. And it looks like there's an atrium in the corner, this red volume that goes from ground floor to the top third floor, and two green corridors perhaps at every floor, right? But there's more to it. Besides the fact that we are abstracting the building, it also has two elements. It's color coded, and it has this strange graph in the middle, right? So I've already kind of gave you a hint of these things. The color coding is a space syntax measure of centrality. And it's not, at all surprising that the atrium is the most central space. It is, from that atrium, you can get to all the other spaces in the shortest way, right? If you're in one wing and trying to get to the other wing, it's a long distance, so it gets a lower score. So the two edges of the wings are the most isolated, so they are in a cool color. And the other ones are graded in between. So how did I get to those colors? How do I get those numbers? Because obviously behind those colors are numbers. There is that graph, that dual graph that is hovering inside that translucent building. So I basically count and do find using depth first search. I do the shortest distance from one point to the other point. You can do it by distance if you want geometry, or you can do it by topology. How many hops do you have to go through? How many nodes do you have to go through? And you can score all of that and come up with a centrality score for a cumulative centrality score for every space, and you color code everything. So that's what Topologic, one of the things that Topologic can do. I have to stop here for 1 second and tell you that when Topologic is a very large piece of software. It's been going on for 3 years. It's funded by the Leverhulme. It was funded by the Leverhulme. Whenever I talk about a certain aspect of it, people say, oh, so Topologic does that. But Topologic does that, and then maybe 3, 4, 5 other things. So it is a platform. I like to think of it as a platform rather than a piece of software that does a specific task. But I have been doing use case scenarios on it and trying it in different contexts in order to exercise its power. But if you ever use it, think of it as a platform on which you build your own domain-specific software. So this is Topologic as well. Now this is Topologic on Blender rather than on Dynamo or Grasshopper. And what this person did, he did like this nice little game, not really a game, like almost like a conceptual design thing, where he basically said that I have this design made out of these 9 squares or 9 cubes. And whenever something is a living room, I would like the walls of that room to be more glass. I want views to the outside. So there are these cubes in the middle that have information embedded in them. We embed information in Topologic in dictionaries, keys and values. So he can change the name of the cube or the attribute of the cube from kitchen to a living room. And the space that this cube is in recognizes that, says, oh, I have a cube in here, and that cube has a dictionary that is a living room. Therefore, I need to change my walls to be glass because that's what living rooms need. And when they are back into a kitchen or a bathroom or something like that, they can change. So you are being strategic. You are designing at a conceptual level. You're setting your shape grammars, right? Your rules about what should happen. And you are letting Topologic look at both topology, at geometry, at semantics, in order to give you the final design. I hope that's clear, but if not, I'm happy to answer questions later on. I shouldn't go much further without saying it's not like a one-person, show here. This obviously we were lucky to be funded by the Leverhulme Trust for I think about £300,000 or something like that. Between 2016 and 2019, I worked with the esteemed Professor Robert H., who is Robert Woodbury knows very well. Of course, they've taught together workshops. That's where I met both of them sometimes. And Simon Lennon, who's my colleague at the World School of Architecture. The three of us were the co-PIs. I kind of took a lead in that project because it was my baby, but obviously the three of us led together. And then we hired 2 research assistants, Katerina and Nicholas. Katerina now is a lecturer with us at the World School of Architecture. We're really lucky to have her. Nicholas moved to greener pastures. He's a computer scientist. He has a PhD in computer science. And he was really one of the main people that developed the the C++ underlayer of Topologic, which we still use to this day. And this project, as I said, finished in 2019. But actually, since then, that's when the exciting stuff happened, because I kept moving it to different platforms and adding more nodes and more capabilities to it written in Python. So now it's actually doing a lot more than it did back in 2019. But yeah, this is a tesseract, just to explain how, what is topology? Topology is the thing that remains constant even in the face of geometric changes. If the things stay the same, meaning what is connected to what, you can have radically different geometry, but the topology doesn't change. The big joke, obviously, is that a donut and a coffee mug are both toruses. They both have the same topology. If you think about them, they're spaces with a hole in the middle. And there are all sorts of things that are topologically identical, but geometrically very, very different. So when I met Robert H., he described a concept called non-manifold geometry or non-manifold topology. Sometimes these things are interchangeable. And like you, I like, what is that? You know, I don't know what he's talking about. But it turned out to be really, really important. So I almost try to explain it to people. If you understand it, great. I'm not a mathematician. I'm somewhere in between. So, but let me explain to you what it is. Most of the CAD systems that you are using use something called manifold topology. A manifold is like something that is enclosed. So think of it as a boundary. Manifold and non-manifold are actually misnomers. There is not manifold and non-manifold. There is two manifolds and not two manifolds, like 3 or 4 or 5 manifolds. So what does that mean? Let's start with two manifolds. If you have imagine you have a simple cube or a simple shape like what you see here on the left side. Every point on that surface is dividing the world that as it sees it into two sets, right? On one side is the interior of that object, the solid, maybe it's made out of wood, whatever that is. And on the other side is the outside world, regardless of how much it is subdivided. But for that vertex, that red point that you see right there, there's only two sets, the inside and the outside. So that is called a two-manifold situation. But if you look at maybe this red dot here on the right side, you will notice that it sits on the boundary between three manifolds. Let's assume this is one object, right? Not multiple cubes, you know, like somehow a set, but actually one object. And those three manifolds is the interior of one of the spaces, one of the cells above it, one of the cells below it, that's the second manifold, and the outside world is a third. So you can have n manifolds, right? And that is called a non-manifold. What does that help us with? Imagine that I'm trying to do an energy model and I need to find a surface that subdivides one space from the other space. I need that surface to be inside my building and not duplicated. I don't want two surfaces because I will have to match them, right? I just want one surface. And I wanted to know that on this side is an office and on this side is a corridor. And that situation, especially the edge of that surface, is a non-manifold situation. So we need to use a non-manifold topology or non-manifold geometry in order to do our work in Topologic. If you look at the CAD kernels, as we call them, the engines that are underneath, many of the same CAD systems have the same, or many of the different CAD systems have the same engines underneath. They are usually classed into either manifold engines or non-manifold engines. So we chose a non-manifold engine called Open Cascade, which also happens to be free and open source, which serves our purposes. And it is able to represent the geometry the right way as we have discussed before. We wanted the geometry to be non-manifold because we needed to do some work with that. So Topologic obviously starts with numbers and math. It builds on top of it a layer of geometry. It builds on top of that a layer of topology, how things are connected. And it builds on that on top of semantics of information that we use dictionaries for. In Topologic, we obviously, in the name, we have to deal with topological relationships. So we represent things all the way from a vertex, which is a point in space, to an edge, to a wire. The wire is a collection of edges that are connected. They don't have to be like head to tail, but they can be any kind of wires. But a closed wire can become a face. If you connect faces together like origami, they become a shell. Like a terrain, for example, can be a shell, or an open cardboard box is a shell. But when you close that shell really nicely, it becomes a cell, and that's our basic unit of a space, of an enclosed space. But we don't make any determination what's inside. The inside could be concrete, could be air, could be void, could be whatever you want. It has an inside, that's a cell. And when you take these cells and connect them together, like soap bubbles, and they share faces, we call that a cell complex. The nice thing about it is that I can ask the cell complex please give me all the cells. And it says, oh, I'm made out of 4 cells. Great, I get all those cells. And they're unique. There are no overlaps. In Topologic, everything is spatially resolved. There are no overlaps whatsoever. But I can also tell the cell complex, I need to paint the interior walls. Please give me all your interior surfaces. And it will give me a unique set of interior surfaces. Or I need to paint the outside of the building. Give me only the exterior vertical surfaces. And it will give me that. So once you have your data structured well, you can get that queries done really, really elegantly. And I can jump over. So you saw that, for example, for a cell complex, I don't have to ask for the cells and then ask the cells for their faces. No, I don't have to do that. I can just simply go for the cell complex and say, give me all your edges, because I want to do a structural model now, and I need all the columns and all the beams and all the linear edges in there. Just give that back to me, or all the vertices, because I want to put kind of like locators or something like that. So you can jump down really nicely. This is we call that decompositional relationships. So as you can see here, this is just a twisted tower of some sort. I can say, give me all your faces. And in this case, they happen to be triangulated. And I said, just explode them a little bit. And I get an exploded set of faces. In this case, I took the torus, which is that gray small torus that you see. And I said, give me all your faces. And again, explode them out from the center. So what you see in the blue is that torus faces exploded out in space. Just to show you that you have full information in there. But then we also have hierarchical relationships, which is really interesting, meaning I can go to a certain vertex, a single point in my building or whatever it is, and I can ask it, what kind of cells use you? Which cells do you use you? Or which shells use you? Or which cell complex uses you? And it will give me back a list of the superior topologies that use it. I can ask that of any of these things. So I can ask a wire what face uses you, what cells use you, etc., etc. It will always know. So our relationships are bidirectional. I can go down, or I can climb up the tree. We also have lateral topology, as I imagined, as you would imagine. So basically, in this, what you're seeing here in this image, it's another one of those test fit buildings. I have a cell complex made out of corridors and spaces and all sorts of other components. And I picked by random, I pick a corridor. I picked this yellow corridor. I highlighted it in yellow. It's exploded so that you can see it, basically. And then I asked this corridor, OK, give me all your adjacent cells. So I call cell.adjacent cells. And it gave me all the cells that share surfaces with it, that touch it, including units or rooms, including the vertical stack of elevators and lifts and staircases, etc., etc. So you can go into any space and just simply click on it and say adjacent cells, and it will give that to you. We can also have lateral topology. I call it lateral topology at a distance. It's basically finding the shortest distance, but it's shortest distance also with a bit of smarts in it, meaning that because there is a graph operating behind the scenes, I can say, how do I go from the room that has this green cube to the room that has this red cube while avoiding the rooms that are crowded and have a lot of these dots in them, right? So you can see that red path that is being drawn is avoiding the cells that have all these crowded rooms. In case of COVID, that would be amazing. I would say, I'd like to get out to my car in the parking lot without going through very crowded spaces. Google Maps does it 100 million times better than I do, but it's available because the graph is there and the semantics are there. So when you build a graph, the nodes in the graph, the cost of going through that node can be represented by the number of occupants in that cell. And therefore, the nodes in the rooms that have no occupants get a better score or lower cost. So you find the cheapest route to go through. Just path planning, normal depth first path planning. But geometry, topology, and semantics all working together to give you the right solution. Also, we have this idea of apertures. So as you can see here in this one, we were going through doors, like through surfaces, through walls, excuse me. But what if, you know, we wanted to go through only through doors? Obviously, we don't want to go through walls. So these yellow things are basically apertures that you can, you know, a special class in topology called aperture that you can add to a surface, and therefore you can find paths that only go through apertures. So I wanted to exercise this thing. So basically, this is one of the models you get from Blender. You know, Topologic now runs best in Blender, but it also is available in Dynamo and Grasshopper. It's also available as a Python module, independent Python module. You can just use it in your software. But you can get these types of things like graph theory stuff, dual graphs, customizable dual graphs, shortest path, centrality measures. As you can see here, the head of this grasshopper is the most central, and the arms and the legs are the most isolated. Completeness, how complete is the graph? Is every node connected to every other graph? And degree sequences. If you read about graph theory, you can get all these things. It's all, we've written all these methods in Topologic. And something interesting is called the minimum spanning tree. The minimum spanning tree is like, what's the smallest graph I can use to connect all the points that need to be connected in my original graph? So what you see here is a, whatever this is, a dodecahedron, or I don't remember what it is. One of those, you know, Buckminster Fuller things. And it is a minimum spanning tree is the yellow, is the smallest graph that connects all the points to each other. So you can optimize paths that way. And graphs don't just apply to like cells and volumetric. This is a graph, as you can see here, of a shell, almost like a cardboard box that's open. And I can tell it that, you know, my unit is the face, and the shared topology is the edge, shared edges between faces. So it works on different dimensionalities. And also it has all sorts of options. Like, do you want the graph to also represent or connect to apertures on the exterior walls, to exterior topologies or not? Do you want to use an internal vertex or just a centroid? There are all, and this actually is a bit old now, it has even increased a little bit more than this, but you can customize the dual graph so that you get information. And all these nodes inherit the dictionary of the parent that generated them. So like if you have a dictionary about the window, you know, it's a double glazing, blah, 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 you know, made by a manufacturer, that red node, that graph vertex inherits that dictionary automatically. So that information is never lost. But then you can just deal with nodes and graphs, you know, without having the burden of dealing with full geometry. So I mentioned dictionaries, and they're really interesting in Topologic because dictionaries are like the DNA of the system, and they actually act like DNA in the sense that they inherit from parents. So dictionaries of parents, or the dictionaries of children, excuse me, inherit and combine the dictionary of parents, and that becomes really important. So for example, in this case, what you see here on the screen, I have a prism, a sphere, and a cylinder. And they have dictionaries that says, I'm a prism, I'm a sphere, I'm a cylinder. When you do Boolean operations, you know, union them, intersecting, subdividing, you know, difference, taking one out of the other, or slicing, we have a lot of Boolean operations that we can do, manifold and non-manifold. But let's take a look, for example, at, you know, merging them or intersecting them in some way. The intersection of the three will have a dictionary that says, I am the intersection of a prism, a cylinder, and a sphere. And if you're drawing like a Venn diagram, the areas of intersection will have those inherited dictionaries combined together. How is that useful for architects? For example, you can have a living room and a kitchen, and you're bringing those two spaces together, and you say, okay, merge them and find the intersection between them. The area in the middle will say, oh, I am the intersection of a living room and a kitchen. And therefore, you can write a shape grammar rule that says, oh, if you find a space like that, which is the intersection of a living room and a kitchen, make that into an informal breakfast area. So the semantics become meaningful in a way. They become useful when you're starting to use this as a strategic document, and you write rules about how you would want to act on certain relationships that emerge from your design.
Wasim,
and that, yeah, sorry.
I think there are some audience here, they may not know what you mean by dictionary. It is a data structure or a abstract data structure that we represent data. Could you explain it a little bit so they follow?
Sure. Yeah, it's a dictionary, a very simple data structure that has a key and a value. So if you are working in a company and you want to keep track of your employees, you will have one dictionary for every employee that says first name John, last name Smith, age whatever 52, etc., salaries and so on. So those things, first name, last name, etc., are called keys, and then John, Smith, and 52 are the values. So you can, in Topologic, create a dictionary by keys and values. You can give it a list of keys and a list of values for those keys, and you create that dictionary data structure. And then you can take that dictionary and embed it inside the geometry. So you can move this geometry around, and that dictionary will just follow along with it. It's just embedded in it. And at any point, I can ask one of those geometries, like the sphere, what's your type? So the type would be the key, and it will answer sphere. I will ask the cylinder, what type are you? It will answer, I'm a cylinder. So you can write data into a dictionary, and you can also extract it out. I hope that's clear.
And it is also performed on the data structure, not on the geometry. Both Boolean operations and the queries, correct?
So our specialized Boolean operations, when we do topologic Boolean operations, they look at the dictionaries and they apply the Boolean operation on the dictionaries as well. Like, it's not just a geometric Boolean, it's not just a geometric intersection, it's also an informational intersection, if that makes sense.
Yes.
Like I combine or I subtract or so the Boolean operations are algebra, right? I mean, you can apply them to information as well as geometry. So as I said, they just think of dictionaries as the DNA of the whole process, and they travel along the process with the geometry, and they get combined and deleted and recombined correctly as we expect.
Thank you, Wasim. It is important to note here that as part of our course and our research as well, representations becomes a very important aspect of what we do. And what Wasim is presenting for the class, this is a note, is an underlying data structure that represents a design idea that can be translated into geometry and topology, and operations can be performed on the now operations are being performed on the representations in the form of data structure.
Correct. But also I say in one of the papers or one of the presentations that information is affected by the geometric operation, but also affects the geometric operation. Let me give you an example. Let's assume you are designing a tower, and in this tower, in the middle, there is an atrium that goes from the bottom to the top, right? It's an atrium. So I've designed my tower using two volumes, one big prism, and then another prism in the middle, which I would like to stay whole because I want it to be like a big atrium in the middle. Now I would like, so I put dictionaries in them. I say, well, the outer prism is offices, whatever, and then the middle one is an atrium. I call it atrium. Now comes the time to slice it to make floors. So I can put horizontal faces in order to slice it. Now, under normal circumstances in any BIM system, if you are not careful, you'll also slice the atrium, right? The slice goes right through the building and slices the atrium. So you get the atrium also made out of like different floors and different stories. In Topologic, you can write a very simple rule when you are doing your Boolean operation to look at the dictionary of the object that you are dealing with. And you can say, if type equals atrium, resist the slice, do not slice, just ignore that operation. So you can just simply go ahead and slice, and then at the end result, you'll notice that the perimeter is sliced into floors, but the center core remains as one whole cell by itself, unsliced. if I just simply go back to the original definition and just switch those over, the dictionaries, right? I give the atrium to the outside and I give the offices to the inside, and I don't do anything else. I just simply switch the dictionaries. At the very end, you'll find out that the boundary was not sliced, but the core was sliced, because you told that these are offices, so they don't resist slicing, and the outer boundary does. And if you say, well, both are atriums, nothing will be sliced. And if you said both are offices, both of them will be sliced. So information in the dictionaries travels with, but also can affect design operations. And that's all built into topology.
Thank you, Wasim.
Yes. May I just make an observation here for the students? Khalil? Wasim is presenting a single instance of a very, very general and powerful idea that every single representation system you will ever use has. And that's the idea that the representation system abstracts certain qualities and guarantees them. So, for example, one of the really important things of an underlying web language you all use, HTML, is its separation of appearance from structure. It's a very weak separation, but in order to understand HTML, you must understand that concept. Now, every single representation in the world has this structure. There are underlying rules that play out in specific ways in the representation. And so Wasim is actually, through Topologic, demonstrating for you a universal property of all representations.
Didn't know I'm doing that, but thank you. One of my styles of presentation is that, I present through examples so that it is ready to hand in a way, kind of ready for the audience to understand it. But yes, Robert is absolutely correct, is that these are always manifestations of general design patterns that you see in other ways. And when I say, Boolean operations as set theory applies to sets, and nobody says what a set is. A set could be geometry, but could be also be tables in Excel, could be anything you want. But the representation of set theories and the operation and the logic behind them and the rules they follow are universal. And that's what I think you need to focus on.
Yeah. I made the observation, just perhaps to help the students. You're seeing a huge amount of concept and complexity presented, but it's an example of thinking about a representation that if you want to understand a representation and use it powerfully, you have to be at this level. It's in your thinking. So as Wasim talks about this very mature and really interesting piece of work, you might try to translate it to other representations you know and ask similar questions.
Yep. Right. So this is just a little bit of a detour, because when I was working on Topologic, at a certain point, Autodesk made a huge announcement that they can do path planning now in Revit, that you can actually find the shortest distance between one and the other. And obviously that sounds impressive, that you can find the shortest distance, but it turns out, and please correct me if anybody is a Revit user, Revit expert, I'm not a big Revit expert. It turns out that you can only do path planning in 2D. You can go from one office to the office as long as those two offices are on the same floor. This is fairly useless. So I took it as a challenge to say, okay, well, if a building is a graph and there is this kind of dual graph, certainly we can, find our way from the ground floor to the top floor. And we should also not just completely go through slabs, we should use the stairs. And if we're going to use the stairs, we should climb them correctly, right? Because in the future, robots are going to be climbing those stairs. So we need to do, correct step by step and do all that. So I took it almost as a challenge, as a bit of a distraction to solve that problem and solve it on on a Revit model rather than just on a conceptual, because everybody can accuse me that I've simplified the problem. So I took a Revit model that I found online, I brought it into Topologic, I rebuilt it, using algorithmic, workflows into topologies. I took the stairs, I built the graph of it, and I combined my own graph, which is a 3-dimensional graph, with what is called a visibility graph, which is a 2D graph, which they have probably used. And I said, well, those are two, one and the same. A graph is a graph, so it doesn't matter if it's 2D or 3D. So I connected those graphs together, and it's really just a matter of merging all the wires together, so that when you're hovering and navigating in 2D, at a certain point, one vertex is connected vertically to one below it, and you can now climb down the stairs. In addition, I took the geometry of the stairs that comes from Revit, and I said, okay, surely in Revit, there is a representation of stairs that says, this is a tread and this is a riser, right? This is the bread and butter of architects. It turns out, no, a stair is just simply made out of these surfaces, and it's up to you to do with them whatever you want. So they use tread and riser to generate the representation, but then they lose it. They no longer preserve that representation in the final object. So I had to take a look at all the normals of all the surfaces of the treads, the ones that are looking up and are within a certain area that kind of look like a stair step. And I created a node for each one of those, sorted them in the Z. I'm sorry, I'm going through that on purpose, just to show you the absurdity of the kind of ad hoc work you need to do in order to build yourself the correct graph, because the information is not saved after it has been created. So I actually took all the surfaces, sorted them in the Z, and built my graph going around the stairs and connected it to the graph, to the entrance to that staircase. And now I can find any two rooms, and the path will go up the stairs, turn around, we'll find the shortest, the closest staircase, and we'll climb up that stair. This is one person doing that, and we have a 50 billion valued company. And I do apologize if anybody's a big fan from Autodesk, but it is shocking how little effort they put into thinking through these representations.
If I may just interpret something Wasim said, that these large software companies that provide services for design, they're inevitably trapped in what you might call a legacy problem. They've got certain ways of doing things that are deeply, deeply embedded in their software, and they're incredibly difficult to change direction.
Yep.
So for example, curved surfaces came out of the automotive industry, and then were embedded in software in through multiple computer-aided design companies. They're a terrible representation for architecture. A much more powerful representation is something called subdivision surfaces, which are discrete tilings of surfaces. Software companies like Autodesk cannot get their heads around subdivision surfaces, even though they provide much, much better tools for making architecture, because they have staff that only understand curves. Their software libraries rely on curves. In order to actually introduce a new idea, they have to invest so much that they won't.
Yeah. I mean, we spend, I would say, 3/4 of our time during the Leverhulme Trust kind of grant years with Robert H. arguing about representation, arguing about naming of methods, arguing about the data structures and what they should and should not do, and of course, all the methods. Because we knew that the moment we encode that and the moment we do one release, we're tied to that. Now, I cannot say that we were perfect because I had to change some things afterwards, but we really struggled with that. Is how do you correctly represent, and how do you correctly name, and what should be the method, and what should be the input and the output of it? Because once you've designed that and you've published it, that's it. You either deprecate it and break a lot of software that is built on top of your software, or you keep it and becomes grudgy and becomes things that are left over in the system, and you replace it with something else. So yeah, it is a really tough problem for these big software companies. I don't deny that. So I've been working with a colleague. He's a Syrian refugee who found his way to Germany. Brilliant architect. His father was the dean of the School of Architecture in Syria at the University of Damascus. He found his place in Dresden, and he's now working for ePro Consult. And they're interested in Topologic, and they're now adopting it in their workflows, and they're doing really amazing things with it. And this one, he took one of those test fit buildings and completely embedded all the information in it using these dictionaries, as I said. And then he can just simply almost like put it on an operating table and just dissect it. Like he can just, anything you want, he will grab out of that building and just kind of like spread it out for you and tell you anything based on a rule or certain relationship or type of object, whatever it is. So I called it the anatomy of a building. And that's the kind of analysis that you should be able to do without building very expensive models. I would call them computationally expensive models. And then we decided, okay, well, it's good that we're doing graphs inside Topologic, but we know that there is software outside that is much more professional than our software in dealing with graphs. Can we kind of hook onto that? And I'm reaching the end of the presentation here. So we took graphs and wrote export nodes to Neo4j, which is one of the leading graph databases, because you can then you can really mine for information. That's what you see here on the right side. And then Neo4j also connects to a really nice plugin called GraphX from Kinevis. So I'll show you what this is. This is the graph of that test fit model. It might not look like it. It will in a second, but this is the graph of it. If you're looking at it like this, it's useless to the human eye, even all the information is in there. But if you say, okay, go ahead and unfurl this graph and put every node where the centroid of the room was, you'll see that it is actually the building. So this is not the building, this is the information of the building. So I can say, give me the balconies, here are the balconies, give me the units, the stairs, obviously vertical, the common areas, the corridors, the garage is at the bottom, there are several levels, and then the amenity space is a couple of nodes in it. All that information is embedded. If you want it three-dimensional and see it in location, that's just geometry. But the connectivity never changed. It just simply unfurled it into its shape. There's another plugin that's called a SemSpect, which is also nice. And again, that reminded me of Rob's pattern on rigs and controllers, because I don't want to deal with the 3D model. I want to deal with a much nicer and simpler logical structure, a controller, that I can manipulate and move, etc. And at any point, I would say, I want to click on that and I want to see the 3D effect of that. I would like to see what the 3D model. We're not there yet, but I'm talking to this company and trying to convince them to connect this software, which runs in a web browser. It's very open, very easy to use, to be able to just simply use it as a controller to the 3D model. And if anybody's interested in working with me on this, absolutely come and talk to me, because I would love for that kind of modern interfaces. And obviously you guys have been doing a lot of work with parallel options and all of these things, so we can learn a lot from that. But we need now almost like a steering wheel for Topologic, and I'm looking at these types of representations as possible ways of dealing with that. So this is SemSpect when it is kind of like all furled. And this is what we have on the left, is what we have in Topologic, which is more display, like you can't really click on them. You need to deal with like the grasshopper type node structure things. This is obviously in Blender, so there's something called Sverchok. And on the right is the SemSpect, which is much more interactive, as you saw. Other areas that we're moving into is graph machine learning, which is really a hot area of machine learning and AI. So we have connected Topologic to DGCNN, and we have a PhD student working on it. And we we are starting to really be very accurate in recognizing from its topology what a building is. You know, hospitals have certain topologies, elementary schools have topologies, towers that are hovering over ground have certain topologies. So we are trying to see whether we can kind of derive what a building type is, because then you can do all sorts of other information on that, just by its graph, not by its geometry or some kind of like image of it. So just some images of that framework that we are working on. And we have a workshop coming up at Cadria that we are going to be dealing with topologic and machine learning as well, if you're interested. So we're generating synthetic databases for graph machine learning training, and then we do predictions. And in the latest paper, we have achieved 93% accuracy. So we're very proud of that. And that's me. Thank you very much for listening, guys.
Wasim, thank you very much. This is a very insightful and very interesting work.
Thank you.
Let me see if I can bring myself in here so you see a human figure. Meanwhile, if you would like to, the audience, if you would like to turn on your videos or voice, please do so, so that it becomes more interactive presentation. We have, let me see, I need to open the chat. Where is this chat? All right, the chat is here. Let's see if we have any questions here.
I see a lot of thanks, so thank you for that. But I would love to hear some either questions or feedback, or open up a bit of a discussion, because as I said, this is ongoing and you can really have a very effective voice in how this is going to move in the future.
Okay. Oh dear, Wasim, it's Rob. I'm going to make a suggestion in the presentation, and that's that slide you showed of the Neo4j database as a cloud moving to the building. You could actually use earlier in the presentation, repeat it later, but to foreshadow things.
Yes.
Say, look at all of these relationships, but what Topologic does is it helps us make sense of them in space.
It was the first slide, actually, at a certain point. But you're right, foreshadowing is really important, as an important technique, yeah.
I just, when I saw it, I went, if people saw this, they might get it quicker.
Yeah, no, I understand. Yeah, definitely. And because Topologic has been going on for many, many years, every time this presentation becomes bigger and bigger. And I'm finding myself now, I need to really talk about some aspects of Topologic and leave some aspects outside. For example, Topologic is very, very useful for energy analysis. Something I did not talk about at all here. It connects to OpenStudio and GBXML and HBJSON. And I talk about that to people who are interested in building performance. But as I said, don't assume, and this is obvious, I'm talking to everybody, don't assume that Topologic is one thing, because it's like a chameleon. It really is more of a foundation.
Okay, Wasim, you made a claim there. It's very useful for energy analysis. From one whole building scientist to another, tell me in a sentence why.
Right. One of the biggest issues with doing energy analysis on BIM models is that they are not energy models that require conceptual non-manifold topologic models. BIM models are not. BIM models, you need to re-enclose and almost rewind the clock to come back with simple zero thickness surfaces. So and if you have just a little gap, all of a sudden air is coming through and your simulation is wrong. Topologic, especially cell complexes in topology, which I use for energy analysis, are guaranteed to be fully enclosed, guaranteed to have full topologic information, meaning a single surface knows the two spaces that it is in, so I can immediately do that. If you look at energy models, they're really nothing more than graphs, and we are very compatible with that. It's one of the earliest papers I've written on non-manifold topology was proving that it works with energy analysis. It was in ASR, I think, that paper.
May I paraphrase what you just said? I'll say it differently.
Please, you say it much better.
I don't know. I'm saying the same thing. Energy analysis involves applying equations of energy exchange. All such equations, convective, which is air movement, conductive, which is the transfer of energy through material, and radiant, which is the exchange of energy between surfaces across space, all of those equations involve directly operate over surfaces. They directly operate over surfaces, areas, lines, and Topologic provides a representation where you can say, yes, that equation, that surface, and other models do not. So it's almost as if there's this beautiful one-to-one mapping between the equations you have to use in energy analysis and the data provided by Topologic. I just said the same thing, but differently.
Thank you. I'm going to listen to that recording later on and repeat it. But yes, absolutely. As I said, two things that we really found very, very compatible is the fact that there is enclosed space, so there is no leakage, and the fact that we have that kind of topologic relationship between spaces that these energy equations rely on.
Now, there is a question in the chat. Any plans to make it open source?
No, we have no plans to make it open source because it is already open source. Yes, of course it is open source. You can find all my horrible Python code and C++ code all on GitHub. Just look at wasimj/topologic. Everything I do is open source, free, forever. Like, it's an AGPL version 3 license. You can just use it. Just don't bundle it and don't sell it unless you want to bundle it and sell it with other open source software. You're free to do that. You're free to use it in any way you want. You don't owe Cardiff University and UCL, which are the IP owners, any money. But just you're not allowed to bundle it with a closed commercial system and then sell that. If you want to do that, come and talk to us and to the people in black suits that are going to be meeting with you. But yes, everything is open source on GitHub.
Some people are interested in if it can be learned by reading documentation or examples. Do we have any documentation or tutorials?
There is, but I have to admit, this is a very sore point with me because we're always looking for resources. I just put in a very small grant now, maybe for a student to come and work with me over the summer to improve the documentation. There is, I have a YouTube channel, which is the best way to start learning Topologic. Look especially at the Topologic sphere chalk. If you're gonna download Topologic, my suggestion to you is use the Blender version. Don't use Dynamo, don't use Grasshopper. Blender is free and open source. Topologic on Blender is free and open source. And it is the best instance of Topologic of the 3 platforms. During the Leverhulme Trust, we developed it for Dynamo first, and then we ported it to Grasshopper. And then after it ended, I ported it to Blender and wrote Python bindings and made it into a Python module. Which opened it up to many, many people because you don't have to recompile, you just simply use Python to interact with it. But documentation is a bit lacking, I have to admit, and videos is the only way I could get there very, very quickly.
Sure. Maybe, you know that we are not, and although we have architects among us in the audience, we are not an architecture school, and our students have interest in designing other things. Or can you elaborate if and how your underlying representations, design representations can be applied, if and how it can be applied to other design disciplines or domains?
Sure, sure. Are people here familiar with a piece of software called FreeCAD? No, maybe not. FreeCAD is built on the same engine that Topologic is built on, which is called Open Cascade. If you look at the Open Cascade website, you'll notice that they have cases from industry, aerospace, product design, GIS, architecture obviously is in there, all sorts of industries that need CAD or need 3D modeling and analysis, including, energy analysis, including FEM, including all sorts of these things. And FreeCAD has also different workbenches that apply for different industries, including even like robotics and 3D printing and laser cutting and all of that. So while I showed some of the possibilities, as I said, it's a foundation. As an architect, I have not delved into all these other areas. All I can say is a similar piece of software that uses the same engine has been applied in these different areas. So there is potential. But everybody will look at it. And if you are interested in proper representation of geometry, topology, and semantics, if your case requires that, I would encourage you to take a look at it and then come and talk to me and see if there is some way we can apply it. Rob mentioned curved surfaces and nerve surfaces, and I agree exactly with what he said. We don't do subdivision surfaces, by the way. We do on Dynamo and Grasshopper support nerve surfaces. When we came to Blender, we were bound by the host, by the Blender platform, which does not support nerve surfaces very well. So I kind of stepped back and said, okay, we're going to then do something where it is pure boundary representation. Everything is straight lines and planar surfaces. And so far, nobody has complained, because as Rob hinted, in our domain, in architecture, we deal 99% with either planar faces or faceted surface subdivisions. And subdivisions is not a problem for Blender, it's not a problem for Topologic. We just don't have the methods to create subdivision surfaces. But if they come in subdivided, we can handle them. I see Arifin is a fan of Open Cascade. I would love to know more about that. Have you used it?
Hi, Dr. Wasim. It's nice to meet you. I'm actually alumni. Rob Woodbury was my senior supervisor for my PhD, and now I'm working for HOK in Ottawa. I've read a lot about you and your works, and it's really amazing, and it's nice to talk to you. Yes, so I haven't started anything with Open Cascade yet, but there are plans which I'm not allowed to talk about, though.
Okay.
But, I'll take this opportunity to ask you about, there was one slide where you said that you would be using the graph representation for generating more models. I think there was one slide there. Can you talk more about that, please?
Not sure which slide. I'll share my screen again really quickly.
Sure.
If you can point me to which, I don't know if you made a note of the.
Is it graph machine learning?
No, it was before that. Although the graph machine learning is interesting as well. And you are using graph?
Let me know when to stop.
Sure.
So I'm going back.
No, not that far back, towards the end.
No.
I'm sorry, I should have taken a note.
Yeah, I mean, I have that's fine.
I'm at work, so I'm having to divide.
It's all right. Not this. This is the final kind of few slides of it.
Right. There's nothing on this.
Not this animation. No?
I think it was this one. Or
Okay.
there was something very similar to this.
Yes. So what I mentioned, not to generate, even though we've done some students attempted that in my MSc for dissertation, is to take a graph and try to generate plans out of it, like actual geometry, and that's a very difficult thing to do. We found
Great.
some ways to do it where we combined it also with machine learning. But on its own, topology by its definition doesn't care about geometry, right? So to go from topology to geometry is really difficult. To go from geometry to topology is straightforward because it's the DNA of it. But to say this node is going to become a well-formed rectangle of some sort, you need more information. We use machine learning and precedence to kind of compensate for that. But what I was mentioning is that in order to drive topologic, we need an abstraction. We need a controller and we need a rig. And that is what I am kind of proposing in this slide on the right side. I would love to be able to have that at the beginning, or at least derived, and then use it to unfurl it and control it and organize it. And then I can click on it and it will highlight, at least minimum, highlight the geometry in my 3D viewport. Or I can highlight the 3D geometry in my viewport and it will immediately dig down into the tree, unfurl it and present it to me nicely so that I can look at the semantic information.
Excellent. So do you mean coordinated multiple views?
Yeah, exactly. But also topology-based coordinated multiple views.
Excellent. Thank you.
I hope to see that from HOK soon.
No, that's great. Yes, thank you.
Thanks,
Arafin, and good luck to you with your new job.
Thank you.
I have a question. Now, this is we are having this presentation as part of a fourth-year course at Simon Fraser University School of Interactive Arts and Technology. And some of our students are possibly considering selecting a research venue as after they graduate, or maybe research-related practices.
Yeah.
So this is definitely coming from a research, as a research initiative initially, and becoming more practical, applicable solution. Can you share your experiences with us as a PI, as a supervisor, or as someone who's working on this research? What are what challenges you have faced when you started this project, how it became an idea, how it evolved to be a tool that you are proudly sharing with the world now?
Sure. I mean, I'll tell you a bit the story of how Topologic came to be. So as I hinted earlier, I was interested in, when I came to the World School of Architecture, the World School of Architecture has a very strong tradition in building science and building performance simulation. Andrew Marsh was there, and they had built this large group doing, building performance. They build their own software as well. I am not a building scientist. I dabble in that. Obviously, my training is more of in architecture and computational design. But when I came into that atmosphere, almost like naturally, I wanted to help. I wanted to connect design to building performance so that designers can get that information early in the design process. So I started, using software to do this, connect conceptual design to building performance. And I did that in 3D Studio Max back, 13 years ago. At the same time, I was obviously following what is happening with the new way of doing computational design, which is at that time generative components. I met Robert Aish. They were doing workshops on generative components. And at a certain point, Robert Aish moved to Autodesk from Bentley, went under the radar for a few years. We don't know what he was working on, and then came back and said, we hear is design script, which is this kind of language that is meant for designers. It's both, what I remember, imperative and what's the other one, Robert? I don't remember the other one. It has two methods, two ways.
Associative
imperative. Yes, thank you. Or declarative and imperative, I think. Whatever. Anyway, so I was interested in what he was doing, obviously. And I went to some workshop that they had done at Cambridge. And then at a certain point, he also did a workshop or a presentation at the Autodesk headquarters in London, the branch in London. So I went there. And that is where he presented a design script And at the very end of the presentation, like within like just 5 minutes, I think he brought somebody from Bureau Happel and said, oh, and also we have something called this non-manifold topology, and you can make energy models out of it. And he showed something really, really small and primitive. But that kind of like immediately like clicked. It's like, oh, I'm doing energy models. I didn't know that this is about energy models. Let me understand what they're doing. And then I made that connection, obviously, between non-manifold topology and energy models. And that excited me, and I wanted to do something with that. So I took design script. At that time, it was connected to AutoCAD, I believe, and kind of like bolted my software onto it and made it work and connected to OpenStudio. And lo and behold, I was able to create an energy model, simulate it, take the colors and show them inside AutoCAD using design script. That worked really beautifully, and I showed it to Robert, who got really excited about it. At that time, unbeknownst to me, they were purchasing Dynamo, right, from Ian Keogh, and moving everything to Dynamo, and design script was becoming the language of Dynamo. And obviously, I don't know what happened internally, what are the decisions, but Robert H. ended up leaving Autodesk and going to becoming a visiting professor at UCL. So in 2013, 2014, you will find public record, you can find it online, me pleading with Ian Keogh, Zach Cron, I believe, Luke Church, all the team that was working on Dynamo, saying, guys, non-manifold topology is really important. What Robert H. was talking about is really important. You might not see it now, but it is important. Keep it in Dynamo. Why is it not in Dynamo? Because it's in design script, it should be in Dynamo. Very polite people, very helpful people, really nice guys, but for one reason or the other, they said, technically, computationally expensive, license-wise, they listed all sorts of reasons. We cannot include non-manifold in Dynamo. And to this day, it doesn't have it. Huge opportunity lost. So out of frustration, I found my research kind of like, as somebody who wants to publish papers and get research funding, that's all blocked. So I went to Robert H. I contacted him. He was at UCL, as I said. And I said, Robert, these guys are very nice. They're very helpful. They're very polite, but they're not going to do it. There's some kind of obstacle. And he said, yeah, I understand why. I said, okay, so how about you and I write a proposal to get funding, and we do it ourselves. We do it in an open source and in a more comprehensive way. He agreed, thankfully, and we started writing it together. And at that time, we consulted with Robert. I think at a certain point, I contacted him and told him about it. We contacted Chuck Eastman, who was still with us, and Arto Kivenemi, if I'm saying the right last name, who was at Liverpool, another BIM person, and to kind of help us, advise us, be our sounding board for this research proposal that we submitted to the Lever. And they helped us a lot in terms of what are the current problems with BIM and how we can address them. And we said, enhancing the representation of space in building information modeling systems. That was the title. We submitted it to the Leverhome. Leverhome has 2 stages, stage 1, stage 2. We passed through stage 1. I was completely surprised because these things are very competitive. Like, ooh, we passed through stage 1. Great. A few months later, we got the letter that it has been approved for £300,000. All of a sudden, we need to do it now, right? That's it. So we quickly assembled, hired the 2 research associates, and sat down. Robert would come from London. We would have, as I said, these kind of amazing meetings. I wish I recorded them. We didn't record any of them at that time. But discussions all day. He would come over and we would have this discussion all day, and then he would take the evening train back to his house. And we were just simply designing it on a whiteboard and saying, what should it be like? And at the same time, Nicholas and Katerina are looking for engines that can be used. They found Open Cascade and starting to learn it, go through the documentation and writing little pieces of software that work and they don't work. And it took us 3 years to get halfway through it. And we ran out of the money and time. The team dispersed, and here we are. And after that, I made it a mission of mine to continue working on it. And I'm seeking support for it from industry, from research councils, wherever. I haven't been successful so far, but I'm privileged because I have a day job, right? So I'm not a startup. I don't need to, answer to investors and all of this. I have my income, I have my day job, and they're kind enough to allow me to work on this stuff. So I publish papers, I supervise research students on it. Now I make it almost like a requirement. If somebody wants to work with me on a PhD, they have to work on topologic or on the robot or on fabrication. So either representation or fabrication. Those are the two areas that I'm interested in.
Excellent. Thank you very much. You are familiar with our research lab in CIAT. It is Computational Design Lab.
I was there many, many years ago.
You have been, yes. Our research is, there are of course some overlaps between our research and yours. We are mostly looking at interacting with design alternatives, particularly led by Rob. And on the other hand, we are also looking at design analytics, analyzing design information by looking at performance and form data. Interesting interfaces coming out. Our research work is looking at collaboration aspect of design data sharing. So let's see if there's any opportunity that we can combine these two research projects. That will be interesting.
Yeah, absolutely.
If there is no, sorry.
Sorry, I was just gonna say, it's not a coincidence that I said I need a really nice interface to Topologic, because I know that you guys have been working on really innovative interfaces on how to access information and how to organize it and how to present it. I haven't done the kind of user interaction and user interface that you guys have done. So I think that would be an amazing magnification of Topologic and how you access. I mean, it just makes it more accessible, I think.
Right. Among our students, some of them are interested in user experience design, user interface design that goes beyond, web page design, of course. Maybe they will be interested in hearing your, maybe being part of your research team. I don't know. I'm just putting, and we are going to share this as part of, I think it will be nice I'm going to post this in our computational design lab YouTube channel, and maybe you can also, if you want, you can post it in your channel as well.
I would love to, yeah.
So we are running out of time. Thank you very much, Wasim, and everyone who's attending this lecture, who's not part of this class, this IAT 437 representation and fabrication course. We are hearing lots of thank you notes on the chat. Thank you, everyone. Wasim, I'm going to leave you your final goodbye words, then I will talk to my students about what we need to do in the remaining of the semester.
Absolutely. I'll leave you with a quote from Bill Mitchell. I invited him to be the keynote speaker for the Acadia conference that I hosted in 2001. And we were chatting about like, I was doing a collaborative system at that point, and it was very slow days, this is 2001. And he said, never design for the current hardware. Design it correctly, and then the hardware and the technology will catch up with you. Right? I think he was probably doing the skate to where the puck is, that kind of a version of that. But he was right in the sense that you design it correctly, and maybe the software and the platforms that you are using are not able to keep up with you. But if you design it correctly, it will find a voice later on. So that's what I would leave you with.
Yeah, I knew Bill a little bit, and that statement encapsulates or demonstrates so much of his thinking, that he was incredibly adept at finding the right idea, expressing that idea, and then saying, well, computation will catch up. So his book, Logic of Architecture, his book, The Reconfigured Eye, are all beautiful and prescient statements of things to come and ways of thinking about things. So yeah, that was pure Bill Mitchell, Wasim.
Absolutely, absolutely. Well, guys, thank you again. Rob, really good hearing your voice. I hope to see you soon. Khalil, thank you very much for inviting me. Everyone, good luck with your studies or careers or whatever you're up to. Good
Thank
night.
you. Good night.
Good night, everyone.
Khalil, if I may just say one thing before I leave you to your class.
You can do one or two or three. You can stay as long as you want, or you
It's a
can.
message to the class.
Mhm.
You just witnessed something extraordinary. You could go to any of the best universities in the world, and at a graduate symposium, you would seldom have a presentation that was so authoritative and clever. So although there was an enormous amount there, I had to work to keep up. I just want you to understand that you just saw something absolutely extraordinary.
Thank you, Rob. I'm going to pause recording. Good conclusion of this presentation. Thank you.